Yeah, Pankaj, you can start.
Okay. So we shall start now. Good morning, viewers. I, Dr. Pankaj from IUAC New Delhi, along with my Inyas colleague, Dr. Pooja from CSIR, CSIO, Chandigarh, welcomes you in the 12th webinar of Insa-Inyas webinar series, Vigyan Setu. Under the Vigyan Setu series, till now we have completed 11 webinars, and most of them have been based on COVID-19, a very small microorganism and its prodigious effect on humankind. As articulated in previous webinars by various speakers, we must not forget the basic science. And today we are in 12th webinar of this series and on an entirely different topic related to astrophysics. In this webinar, we will discuss the effect of gravitational attraction, cosmic illusions, India's mega science plan to observe and study gravitational waves and their production due to distortion of space and time, how India plans to build a laser interferometer gravitational wave observatory, LIGO India, and what would be our expectation from LIGO. Friends, today we have with us Professor Somak Ray Chaudhary. He is director of IUCA Pune, and he will talk upon Einstein's outrageous legacy, cosmic illusions, and gravitational waves. I request our viewers to post their questions related to the topic on YouTube chat box, which we will be taking with the speaker after the talk. Before we start the webinar today, it is our pleasure to have Professor Chandrima Saha, President INSA. I request you, ma'am, to introduce today's speaker. Professor Saha, please.
Thank you. Can you hear my voice?
Yes, we can hear.
Okay, good morning, everyone. And I shall start wishing you a very safe time during our fight with COVID-19 and warmly welcoming Professor Somak Ray Chaudhary, an eminent astrophysicist. And it is really a delight to have you with us, Professor Ray Chaudhary.
Thank you. It's my delight.
When we started this Insa-Inyas webinar series, we primarily focused on issues related to COVID-19, as Pankaj alluded to, because there were a lot of questions to be answered through science. And I'm afraid there are still issues that we do not understand, and it is an evolving situation. Like the very tiny virus, which is about 1/1,000,000th of an inch in a world that cannot be seen by the naked eye, we have our universe, where also unseen to us, mysteries unfold. So astronomy is the study of an infinite majesty of the universe. And I'm sure that Professor Ray Chaudhary will leave us through the excitement of the study of the astrophysical phenomenon. I shall give a brief introduction to Professor Ray Chaudhary. He is the director of the Inter-University Center for Astronomy and Astrophysics, shortly called IUCA in Pune. He graduated from Presidency College, University of Calcutta, with further studies at University of Oxford in UK. After his doctoral studies from University of Cambridge, he had a stint at Harvard Smithsonian Center for Astrophysics in USA, where he was a part of a team that built the Chandra X-ray Observatory for NASA. And it is now celebrating 20 years of existence in space. After teaching for over a decade at the University of Birmingham, he returned to India as head of the physics and dean of sciences at Presidency University, Kolkata. And after that, he became the director of IUCA. Dr. Ray Chaudhary is a fellow of the National Academy of Sciences, Royal Astronomical Society, and the Astronomical Society of India. His research involves a wide range of topics in cosmology and astrophysics, from the ground to the space. And today I welcome Professor Ray Chaudhary to deliver his lecture for us. Thank you.
Thank you very much indeed, Dr. Thank you for that amazing introduction. Shall I share my screen right now, Dr. Pooja?
And now I formally request you, sir, to deliver today's talk.
Thank
you, sir.
Can you see my screen now?
Yes.
Yes, we can see.
Yeah,
Please go ahead.
you can see it.
Wonderful. So I thought, again, thank you very much, Dr. Shah, and everybody else for asking me to be here. I just, of course, want to take your mind off the raging pandemic outside our doors. And in particular, I'm sitting in a place in Pune where it is very hard hit by the pandemic. But I think I'm glad we are coming out of it. And one of the things that we have learned from this situation is that we can engage in these activities where we can give talks sitting in our office, and then it can reach a lot of people, not just across the country, but across the world. And so let us talk about Einstein and what he taught about us about the universe. And what I'm going to do today is I'm going to talk about Einstein's way of looking at gravity. The title of my talk is inspired by the subtitle of this book by Kip Thorne, Einstein's Outrageous Legacy. What I'm going to talk about is how Einstein thought about gravity and how it departs from what we learn in school, which is gravity as conceived by Newton. And I'll talk about two aspects of it, because there are many, many things that Einstein's new idea about gravity 100 years ago actually leads to. And one of them I'll talk about is gravitational lensing, which was seen, effects of that was seen in Einstein's lifetime. And then I'll talk about gravitational waves briefly, where this is an effect that Einstein predicted, but could not see in his lifetime. It only we saw its effect 100 years after the theory came out. So the idea is, what is gravity? As we all learn in school, Isaac Newton described gravitation as an universal force that acts between all objects that have mass, any two objects that is massive, and can pull each other by this force depending upon the mass, which is proportional to the mass, and inversely proportional to the square of the distance. And this, being a force, causes things to accelerate and causes motion between the objects. Now, this theory has been applied to describe the motion of almost everything around us, and it works very well. We can send satellites out into space and visit other planets based on this basic formalism that Newton laid out. But there are certain things that this theory cannot explain, which prompted Einstein to think about whether this is the full explanation of gravity and whether it is a subset of a bigger explanation. In particular, when things are traveling very close to the speed of light, or when things have very big mass, and then there are very tangible departures from what Newton's theory predicts. And so Einstein actually changed the whole way of looking at gravity. Instead of thinking of it as a force that acts along the line like an invisible string between two objects, he thought about a more local phenomenon. Einstein's idea was that in order for certain things to happen, for example, if things are moving very fast, the communication between the two about the nature of the force and the direction of the force can actually be very difficult to explain in terms of Newton. And so he made it into a very local phenomenon. Einstein's idea was that if something has mass, the space around it, he called it space-time, actually gets curved. And this curvature of space-time leads to an effect that looks like an attraction between the two objects. So it's actually the distortion of space around a massive object that is the main effect of mass, rather than actually a force. And then due to the distortion of space-time, the other objects around this object move in this space-time according to a certain formalism that he laid out. And so gravity is not a force, it is actually an effect that causes things to move around paths in curved space-time. And by straight paths, I mean they follow a natural path between 2 points around going by the curvature of space-time. So the idea is that, for example, the sun being a massive object distorts the space-time around it. So space-time, if you can think of it as a thing, as something that has a presence, bends around the sun, and the Earth, for example, which is going around the sun, is going around it because it is trapped in this curvature of space-time, and so it goes around along this curved space-time around it, right? So this has very wide-ranging implications. For example, has an implication about how light travels in the universe. In Newton's formalism, light has no mass, and so gravity cannot have any influence on light, and so light cannot travel, cannot be affected by gravity. But for example, if you have along space-time a light ray coming from one end of it to another, and there is, due to the mass of an object, intervening object, a curvature in space-time, light follows this curvature of space-time, and it follows the shortest path between 2 points along that space-time, along that space, and so it would curve. So in Newton's theory, light cannot curve. Light's rays are straight, whereas in Einstein's theory, it can. And it leads to very interesting effects. For example, if you have a star and an astronomer studying a star through a ray of light that goes along this curved path, then the astronomer will see the star there. And so it causes a cosmic illusion. And so this actually was predicted and tested within 4 years of the theory coming out. Einstein's theory was published in 1915, and people started thinking. Of course, then First World War was going on, so it took a while for the theory and the paper to reach other people, particularly to the non-German speaking world, because the paper was published in Germany in German, and Germany was at war with the English-speaking world at that time. And so it slowly filtered out to the rest of the world. And then very soon came ideas of how to test the difference between Einstein and Newton. And the person who did this the idea was that you would see that if you had a picture of the stars around the sun, then because the sun's gravitational field would curve the space-time around it, from the Earth, you will see the stars at very different places, depending on the position of the sun. So as the sun moves around the sky, you would see the stars behind the sun displaced, right? So how would you do that? The problem is, of course, you can't see the stars around the sun because it is during the day, and in the day you don't see the stars. So the stars are there, but you don't see it because our atmosphere fills it is filled by the scattered light from the sun, except when the sun is covered. If you cover the sun, which happens during a solar eclipse, then you can see the stars around the sky, around the sun. And this was a fantastic idea that Arthur Eddington came up with. And so in 1919, barely 4 years after the theory was published, Eddington realized that the sun is going to be eclipsed by the moon. And you could see it from the coast of West Africa. And Arthur Eddington led an expedition. It took a telescope and took pictures of the stars around the sun during the eclipse from the island of Principe of West Africa, and then compared it to a picture taken 6 months later of the same place when the sun was at the other part of the sky, and found, of course, that during the eclipse, the stars had moved out. So they were seen at a different place when the light rays were passing the sun, and the sun was in the foreground. So exactly what Einstein had predicted. So when he published this result, Einstein was very, very happy. And he wrote to his mother a postcard saying, "Dear mother, my theory has been now proved by somebody else." And this is this childlike happiness, very rarely seen nowadays in scientists. I suppose when somebody's theory has been validated by somebody else, I don't see any scientists around me who write to their postcards to their mother anymore. So this was a momentous occasion in which, the first time it was shown that this new idea that Einstein had, which differs from what Newton had taught us, actually can leads to an experiment that can be proved. So then, since then, a lot of interesting things have happened. This particular experiment led to a whole new subject called gravitational lensing, showing that what we see in the universe is actually distorted by the presence of matter in the intervening space between us and the star or the galaxy that we are seeing. And this is known as gravitational lensing, which leads to one of the terms in the topic of my talk, cosmic illusions. So we see cosmic mirages on a big scale. The universe is filled with dark matter that we don't see, so we don't know that it is there. In particular, the matter is there in between the galaxies, in a cluster of galaxies. If there are in dark halos around galaxies themselves, they are in all forms. They are in the universe, and what they do is this matter, due to the gravity of the matter, light rays coming from distant galaxies, distant quasars, distant sources, pass through this matter, and this matter causes the space-time to bend, and as a result, we see them distorted. So here we are from the Earth in the Milky Way, and if we are looking at a galaxy very distant, the light rays that are coming to us from all kinds of directions can bend, and we see them at different places. Here is a cartoon showing how this can be done. For example, if you have a distant galaxy and there's a lens galaxy. A lens galaxy is what causes the distorted space as well. So the light bends. This is exactly what a lens does in a telescope, for example, or a microscope. So what will happen is that the light from this distant object will bend, and you will. Yeah, let me share my screen again.
Yes, please.
Can you see the screen?
I can see the screen. I can see the screen.
Okay. And you can hear me?
Yes,
Yeah,
clearly.
please.
Great.
Please.
I don't know what happened. It just the meeting ended. So are you making it live now?
Yeah, it's live. Yeah, I resolved it out. Yes.
Okay.
Okay, thank you. I'm very sorry for this interruption. Let me continue my story about gravitational lensing. What I was saying is that if, for example, as I said, a massive object like a galaxy can act as a lens. And so when we are looking at something that is completely a source of light, which could be a distant galaxy, which is completely aligned on the same axis with the lens, with the light that comes to us is equally bent along all directions, and so it will appear as a ring. So this is something also that came out as a prediction from Einstein's theory, that if a source is completely aligned with something in the foreground that is massive enough to bend the light, then you can get light all around and it will act as a ring. These things were discovered for the first time, not in Einstein's lifetime, but in the 1980s and 1990s. Now we see them, for example, in large telescopes from the Earth and in the sky from the HST, for example. You can see the image. It's a cosmic mirage, really. It is an illusion. You see a galaxy that has been stretched. And so the blue fuzz that you see is a galaxy in the foreground, and you're seeing a galaxy behind it, and you see it in the form of a ring. And it is actually a galaxy that is a tiny blob like this, but you can see it because light has been bent around it. And if it's slightly offset, you can see a broken circle like this, etc. And if it's a little more offset, then this circle breaks up into multiple images. Also, if the source is not a point but an extended object, then you see it highly distorted in various forms around the galaxy or the cluster that is in front, which is causing this deviation of light rays. And here's a good example of the cluster ABL 2218, Hubble Space Telescope spectacular image, in which you can see all these little galaxies that are distorted. Sometimes you see multiple images, this galaxy and that galaxy of the same galaxy, but seen in two different places because of the light that comes from them is being deviated by this cluster of galaxies in front of them. In fact, in this particular image, there are 100 examples of distorted images of galaxies. From this, you can figure out how much matter there is in the universe, because you can ask the question, to cause this kind of distortion, how much matter do you need? And apply a simple optical experiment and then figure out how much matter there is. So this is our primary source now of learning the matter content of the universe. And here are spectacular examples of this gravitational lensing that what you can do with the great telescopes, either the Hubble Space Telescope in the sky or telescopes that are at very good sites on the Earth, like the Subaru telescope of Japan. So I told you one effect that this curved space-time has. Now, what happens is that there are these very, very dense objects in the universe called black holes. And black holes are very exotic objects. They come from the fact that you can collapse an object to a very small amount of volume. They can be understood, for example, by from Newtonian gravity, but the actual quantitative description has to come from Einstein's equation. If, for example, you know that in Newton's theory of gravitation, you have a concept of escape velocity, which means that to escape from a gravitating object like the Earth, you need a certain velocity, which is given by this formula 2gm/r square root, which just tells you that if you have an object like the Earth, for example, which has a mass m and a radius r, then you need a certain amount of velocity to escape from it. This means to overcome the gravity of the Earth. This is what you use in, for example, spacecraft that want to go away from the Earth. Now, imagine now that velocities cannot be arbitrarily high. The maximum velocity that you can achieve is the speed of light. So, for example, if the escape velocity of something is greater than the speed of light, then nothing can escape from it. And so that is how you can, even from a Newtonian concept, you can understand black holes. And so in terms of Einstein's idea, you can, as I said, you can think of the space-time being curved by a particular mass, but you can think of something that is very, very small, but also extremely massive, can curve this space-time so much that it turns into a well from which even light cannot escape. So that is the Einsteinian description of a black hole. And what we can do now is look at a simple application of Einstein's equation gives us this equation called the Schwarzschild radius, which means that if you have an object that has a mass m, then it can turn into a black hole. If, for example, it can be squeezed into a space that is so small, which is given by this formula, the Schwarzschild radius, that if it can be squeezed into that kind of size, then light cannot escape from it and it becomes a black hole. So, for example, and of course, not everything can be squeezed in this. I mean, I can turn into a black hole, but I have to be squeezed into a really tiny space. The Earth has to be squeezed into, as you can see, 2 centimeters, a sphere of 2 centimeters for it to become a black hole. Nobody can do that. A sun has to be squeezed into something that is about 4 kilometers across. And we know of processes that can do it. The sun will not become a black hole, but more massive stars, when they collapse at the end of their life, at the end of their nuclear fusion period, they can turn into black holes. And this is something that Subramanian Chandrasekhar showed in the 1930s, how this can happen. And so we know now that in the galaxy and in other galaxies, there are various kinds of black holes. There are black holes that are between 3 to 100 times the mass of the sun. We have been detecting these black holes maybe 3 times, 4 times, 10 times, 20 times the mass of the sun through various kinds of observations, dynamical observations, then X-ray observations for the last 20 years. And these are called stellar mass black holes. And at the other end of the spectrum, you have a supermassive black hole in the center of every galaxy. And these are a few million to a few billion times the mass of the sun. And we don't know how these things form. We know these things form from stars dying, but the most massive stars that we see around us are 100 times the mass of the sun. And so necessarily the stellar mass black holes have to be smaller than that. And then now we can see these supermassive black holes that are 1,000,000 times the mass of the sun, or up to 1,000,000,000 times. So if we have to form these supermassive black holes from the merging of black holes, which are smaller, there have to be black holes in the middle, which are a few thousand times, 10,000 times. And this have not been seen in the history of astrophysics until an announcement came a couple of weeks ago. And I'm going to briefly mention that. And so now we know that there are black holes that are, whoops, what's happening? Am I still audible?
Yes, sir, you are audible.
Yes, you're audible.
Yeah,
Yes.
thanks. We now know that there are black holes in the middle that are in the range of between 100 times to 1,000,000 times. We've just only started finding them. As you know, the discovery of gravitational waves 100 years after Einstein happened and was announced almost exactly about 5 years ago. And that led to immediately the Nobel Prize awarded to the LIGO project. And this led to also the approval of building a LIGO detector for detecting gravitational waves in India. And this is something that we are involved in, and I'm going to talk about now. So the idea is that in Einstein's prediction, as space-time bends around a mass, light bends, as I showed you. But there is another prediction, and that is in this kind of space-time, if an object moves or two objects move and they merge together, then that causes, just like when on water a duck moves, there are ripples on the surface of a pond, then there will be ripples that will travel on the surface of space-time, on space-time itself, everywhere around an object if a very massive object moves. In fact, when I move through space, I'm setting out ripples that go along space-time, but that is too faint to be detected. But you can hope to detect the ripples in space-time due to very massive and compact objects like black holes, for example. But Einstein in 1916, a year after he published his general relativity, wrote a paper saying, actually, this is not going to happen because the amplitude of these detections is going to be very small. The way we do it now, and about 100 years later, of course, this was detected. The way it was done was using what is known as an interferometer. Students of physics amongst us would have used interferometers, a Michelson interferometer in their physics lab. You know that if you have an object where a laser light can come and it's split into two perpendicular beams reflected off mirrors identical distances away, and they come back and combine, then you can have interference fringes. And as long as the two beams of light that are created from the same original beam can come back along identical paths, they create an interference pattern. And what will happen is, as a gravitational wave passes through space-time, it distorts space. In one direction, it causes a compression. In the other direction, perpendicular direction, it causes an expansion. And so what will happen along an interferometer like this is that one of the paths is going to be compressed the other path is going to be extended, and as a result, the balance between the two is going to go, and so from the resultant fringes, you will be able to detect that such a thing has happened. Now, there might be many other effects that will cause this as well, but the signature from gravitational waves is very unique, and it can be distinguished from all other forms of that can lead to such shifts in. But the problem is that this effect is very, very small, and it's for a gravitational wave detector that is a few kilometers long, like LIGO is. The displacement is of the order of 10 to the power minus 18 meters, and this is what led to Einstein to say this is never going to happen. Just to show how small this is, human hair is about 100 microns, and that is 10 to the power minus 8 meters. You look at the atomic diameter, it is 10 to the power minus 10 meters. Human hair is 10 to the power minus 4 if it's 100 microns. Wavelength of light is going up to about a micron, with which you see through your eyes. But the nuclear diameter inside an atom is 10 to the power minus 15 meter. And what you're trying to do is you're trying to detect something that is 10 to the power minus 18 meters, that is even smaller than the size of the nucleus in an atom. How do you do that? And this is a fantastic experiment, the LIGO experiment in the US, that has managed to do this, which led to the Nobel Prize, where due to this kind of an arrangement of an interferometer in two places in the US, in Hanford in Washington State, and in the Livingston Observatory in Louisiana, for the first time, which is 3,000 kilometers apart, for the first time in 2015, a gravitational wave was detected at the same time by two different observatories. As you can see, the arrangement of the interferometer, which is 4 kilometers long along each axis, that led to the discovery of the difference between the two arms being contracted and expanded by about 10 to the power minus 18 meters. And so this is an amazing experiment that showed us our first discovery in September 2015, as you can see, exactly 5 years ago. And this whole thing happened as a result of two black holes merging. They went around each other and merged, and the whole time period of this observation is 1/5 of a second, 0.2 seconds, as you can see from this x-axis. And what happened is that the frequency of the gravitational wave, as the two black holes merged, went up, and within that 1/5 of a second, and you can see the frequency going up, and that's a characteristic way of nothing else produces something like that in such a short amount of time. And so it turned out that the black holes that were discovered in this process had masses of around 30 times the mass of the sun, each 28, 29, and 35 times the mass of the sun. So very massive, making a 60 solar mass black hole. And their sizes, the Schwarzschild radius is shown very nicely here, would be if you have a 62 times the mass of the sun black hole, the actual size of that black hole would be the size of one of the states of India, and just a very nice way of graphically showing these were very massive black holes, not really the ones that we initially were discovering before then, which were a few times the mass of the sun. These are already getting into 30 times or 60 times the mass of the sun. So this was the first discovery. Since then, LIGO has announced close to 70 such measurements in the last 5 years, and there are many others that are being analyzed. I'll give you examples of two things that have been shown by LIGO, which are very interesting phenomena, and before talking very briefly about what we're going to do in India. So for example, this particular object that was discovered in 2017 were actually the merger of two neutron stars, not black holes, but these are stars that are 10 kilometers across, made entirely of neutrons. They are very compact, almost not as compact as black holes, which are much smaller have stellar masses but are much smaller. These things are about 1.4 times the mass of the sun, but they're 10 kilometers across, and they merge. And in this particular case, what happened was that this is the only case so far out of the 70 cases that we're talking about, where we have seen when this happened, not just gravitational waves coming from it, but other forms of light, actually optical light, as well as X-rays, gamma rays, etc., coming from it. And here is an example. It actually led to this is the corresponding event in an optical picture where it happened, and it could be pinpointed and found, because there was so there was a big campaign then, as you can see, in all kinds of electromagnetic waves, gamma rays, X-rays, UV, optical, infrared, radio, which looked at the same place. Once we found, we knew where this happened, because normally in the LIGO events, we don't know where this gravitational wave is coming from. There's a very big uncertainty. But in this particular case, we knew where it was coming from. The interesting thing is, why is this interesting? Because when two neutron stars merge, the kinds of temperature and pressure that it creates some very exotic elements like gold and silver. In fact, almost all the gold that is in the universe is made from collapsing neutron stars that are merging together. In fact, if you are right now wearing a gold a ring or a necklace or something, know that all those atoms in your ring or your necklace will be made in two neutron stars merging somewhere. And they will send out a gravitational wave like the one we saw here. So we have to find out about these things. It's a very unique event that we saw. Then there was another event that was announced just recently. You might have read in the papers, 1905-21. Only a couple of weeks ago, this was announced. And this was the most massive object that has been found so far in the merging black holes. One found the gravitational wave due to two black holes, one 85 solar mass black hole 85 times the mass of the sun, the other 66 times the mass of the sun, merging together to form something that is 142 times the mass of the sun. This was the first time something larger than 100 times the mass of the sun has ever been found. And this kind of showed us how we can actually build bigger black holes by merging smaller and smaller black holes. So these are the ones, for example, if you look at the black hole masses on the y-axis, previous black hole mergers that have been seen, and we've been seeing bigger and bigger and bigger black holes, but this was really the bigger of them all. And you can see how you can hierarchically merge smaller black holes into making bigger and bigger black holes. That helps us understand how very, very massive black holes can come into existence. This is a very nice little plot where on the y-axis you see the number shows you the times the mass of the sun, the black hole, and this is the latest one, the most massive that's ever been found. All the blue ones are the ones that have been found from gravitational waves, whereas all these purple ones are the ones that have been found earlier, before LIGO was found, and these are the ones that have been found, which I haven't talked about how they've been found, but they've been found mostly by the Chandra Observatory from X-ray observations. And these are the masses of the neutron stars that have been found so far. And so you can see we are now, with the gravitational waves, finding a totally new kind of object. And this helps us understand the implications of this outrageous theory that Einstein had. So right now, there are these two gravitational wave observatories in the US that are operating, and actually one in Europe that has come online in Italy that are working together. In fact, the last one I showed you, the GW19, that was found by all three of these observatories together. And then Kagra, which is another gravitational wave observatory in Japan, it's about to come online and was almost starting to work before the pandemic shut everything down. And so they will join. And then we are planning to build something here in the center of India called LIGO India, along with the people who have built these two observatories. In fact, they built 3 sets of detectors, and the third one, which was not installed in the US, they are giving to us as a collaboration between India and the US in this amazing mega project in which India will have to build the infrastructure in the middle of India. And this is the now the blueprint of what it's going to look like in the middle of Maharashtra. This is the 4-kilometer arms and the central station in which the two laser beams are going to come and meet. This diagram has been prepared by DCACM, which is part of DAE, the civil engineering part of the Department of Atomic Energy, who has in charge of actually building the civil infrastructure of this place. The collaboration between the US and India. On the Indian side, there are 4 institutions that are in charge of building this. The 4 institutions are shown here. This is where the LIGO India will be built in the Hingoli district in Maharashtra. And the 4 institutions, my institution, Ayuka in Pune, is the science stakeholder. We're going to look at what science is being done with LIGO India, and also look up to the computing requirements, and also building the manpower that will actually run this observatory once it's built. Actually, the building process from now till about 2026-27 is going to be taken up by the IPR in Gandhinagar, who are experts in vacuum, because these tubes have to have nanotor vacuum in them. They're extremely evacuated. And RRCAT Indore is going to build all the laser infrastructure as well as the suspensions, and DCACM, the civil infrastructure. It's already, the land has been acquired. This is where we see the main people from the 4 institutions standing there, where the 2 arms are going to meet in this place. You can see the land is very much up and down, so it has to be leveled. A huge amount of civil work needs to be done, but the land is now completely acquired. We are waiting for the cabinet nod for the main part of the funding to come. Now there is quite a lot of seismic tests going on there, and also testing the rock and the soil around it to see whether what kind of noise we will have in the site. The site turns out to be wonderful. And you look at the amount of intricate kind of technology that this involves. A LIGO mission, nothing like this on this kind of scale has been built in India before. And we have to build all this kind of infrastructure where the mirrors involved are suspended in a sense where the external vibrations don't affect it, and it's going to be in high vacuum. So this is a huge challenge in technology for India now to build this. What we're also doing is this around the site in the Hingoli district, we are in a massive outreach effort to involve the people who live there and the school children, and to educate them about astronomy as well as LIGO. And we have a team, a wonderful team, who go around looking at, here is, for example, a picture in which all the school children have been asked, who wants to be a scientist? And they are raising their hand. So there you are. So we are trying to reach out to everybody. And we are very active on social media. Look us up on Facebook and Twitter, and you can hear about what is happening in LIGO India. So it is being led by DST and DAE in the construction phase, and then Ayuka is going to look at running the observatory after it is built. I will leave you with the names of some books that you can follow up on what I just said. You can read about Einstein in his best biography by Abraham Pais, and also these are good books about black holes and gravitational waves. I'll stop here and see what discussion comes out of it. Thank you very much.
Yeah. Thank you, Professor Chaudhary. It's really an amazing talk, and I'm sure that our viewers might have benefited. And Pooja, would you like to take first question?
Yeah, sure. First of all, I thank you, Professor Somak, for such an informative and fascinating talk, covering so many aspects of gravitational lensing, black holes, and LIGO project. So now we will take few questions. The first question is, gravitational field is determined by the mass of an object. So bigger the mass, larger is the gravitational field. On the other hand, the intensity of gravitational wave will also be determined by the distance of an object from Earth. Is LIGO armed to distinguish between size of object versus distance?
Yes, of course. I mean, of course, the problem is in astronomy, this is a major problem, is to find out how far away things are. And the effect of anything, even if it's in gravitational, in electromagnetic waves, it falls off with distance. And so, for example, it is difficult to distinguish between something that is faint and near us and something that is very bright and very far away, right? And we do that by either trying to figure out some way of measuring the distance to the object, or knowing how big something is through some other means, right? So, for example, if it's to do with the sun and the moon, they look like the same on the sky, but we know how big the sun is from some other arrangement, from some other inference, and thus we know that the sun is further away from the moon. So in this whole structure of the wave that I showed you, there is a lot of information. There's a lot of information about the mass of the objects. And then we also know how bright the object is, or how much of the energy that we are receiving on the Earth. And so we can combine the two to figure out how far away they are. And so we can distinguish between a merger of two black holes that are forming in our own galaxy and a merger of two black holes that are in a galaxy very far away, just by knowing what their masses are, and because of the waveform, the shape of the wave tells us that, right?
Right, sir. So before we go to next question, I would request you to stop sharing screen so that we can see you clearly. Yeah, Pankaj, please.
Yeah.
Go ahead. Okay, so I will take next question again. The second question is related to cosmic gravitational waves that reach Earth and which then be picked by a LIGO detectors are only a fraction of the total. How would the researchers assure that it's not the noise, but they are what LIGO is picking up?
Very, very good question. Because as you see, I mean, the signal that LIGO is picking up is very tiny. As I said, 10 to the power minus 18 meters, even for something that is so big. If it's a smaller object, a smaller detector, then the signal is even smaller. But if you go near a gravitational wave detector like LIGO and drive a car, or even jump up and down in the building, you create vibrations that are much, much bigger. Also, within the system, you can have, as the laser light hits the mirror that is and gets reflected, it causes thermal effects that cause vibrations or cause distortions that are bigger than the effect that is being measured, because the thing is much smaller than even the atomic nucleus. So these are all sources of noise, sources of mechanical noise, seismic noise, for example, which is sort of earthquake-like, not earthquakes, but small. In fact, when the first the gravitational wave was detected in 2015, we worried whether at that time we detected a thunderstorm that was happening in Nairobi, right? So far away, because you could actually detect that. You can detect every single wave that hits the coast of the country by this gravitational wave detector, because the continent vibrates. But all of these things have their own signature. All of these things their vibration looks in a particular pattern, right? The way gravitational waves are detected in the sea of noise, the noise is much bigger than the signal, which is not always the case. Normally we have signal bigger than the noise. Here the noise is much bigger than the signal. And the way we measure the signal is actually a technique that was devised here in Pune by Sanjeev Dhurandhar and Satya Prakash, who wrote this first paper to show that you can do something called template matching. You know templates of things that you're trying to detect, and you know the templates, the kinds of vibrations that come from the noise, and you match them and figure out whether you are detecting something that matches exactly the kind of signal that you're looking for. Right? So this is how we distinguish between noise, because we know the nature of the noise, we know the nature of the signal, and we can find exactly the profile of the signal in the haystack, of noise.
Right, sir. So it's very interesting to know about it. So now I'll move to next question. The next question is, can LIGO interferometer work efficiently in the presence of seismic noise waves? Can such events lead to misleading signals?
Yes, so this is one of the things I talked already, and
Yeah.
this is why we need to know the basic seismic environment of the observatory very, very well, and this is being done now. In fact, we found in our initial tests that the seismic characteristics at these frequencies are like 1 hertz, 10 hertz, and things like that. Seismic characteristics of the Deccan Plateau in the surroundings of the Hingoli district is about 10 times better than anywhere in the US. So we know that we are in a seismically, because the Deccan Plateau is a very, very stable part of the earth. Whereas, as you know, the seismic characteristics of the United States is actually there are quite a lot of seismic activity going on. So the people who built the original LIGO detectors were very, very impressed to see that in India we have a site like this where it is very quiet. But isolating, so a lot of things that I didn't show in the construction of LIGO, all the optics is isolated from the surroundings by suspensions that take this into account, vibration isolation. It's a topic of its own, which is fantastic. Now, even though you take all these precautions, it can couple with the vibrations outside, and so it is important to have a place that is seismically quiet. And also, we know when such an event happens that the earth is vibrating, we know exactly what it looks like, and we won't mistake it for the gravitational wave signal, which has a characteristic pattern.
Right, sir. We have received a lot of questions from viewers. So now we will go ahead with the questions from them.
Yes.
So the first question is, one of the Newton laws say an object at rest will remain at rest. An object in motion will remain in motion until and unless it is compelled by an external unbalanced force. Does it apply to space-time?
Oh yes, of course. I mean, those are not the Newton's laws that Einstein changed. The three Newton's laws that we learn in school about, the first law being inertia, what you're talking about is inertia. Second law being that the force is proportional to acceleration, and third being action and reaction being opposite. Those three are unchanged. The law of gravitation that Newton found was F equals gmm over r squared, which is the next level of Newton's laws, and that is the nature of the force. And Einstein elaborated that nature of the force. But the nature of inertia, the nature of how interactions happen, etc., all these remain unchanged. So nobody's changed those Newton laws of Newton.
Right, sir. Yes. So going ahead with the next question from Upasna. Okay. There is another question from Saurav Biswar. So Upasna question you already covered, sir. Saurav is asking, why does object moving in trajectory, the objects that are in rotational motion break towards the east?
I don't understand that question.
Okay, then I will request the viewer to reframe this question. Yeah. I will pick this question again. So moving to the next question, again from Upasna. Are black holes also in motion, since black holes have immense gravitational force such that nothing can escape? Is there any remote possibility of the sun getting engulfed by a massive black hole?
Okay, there are many questions in there. First of all, of course, black holes are in motion. I showed you that there are black holes that are going around each other and merging together to form a bigger black hole. Everything is in motion. Nothing is static in the universe. And gravitational waves are produced when these things move through the universe. So when a black hole moves through the universe, it creates ripples, and that's what we are getting as gravitational waves. If the black hole was static, then there would be no gravitational wave from it. Okay, so it's the dynamics of the black holes that are important. And the second thing is, I don't think you should lose sleep at night thinking we are going to be engulfed by a black hole. In fact, even if the sun today turns into a black hole, nothing will fall into it. The black hole, the effect of the black hole is only seen only a small distance away from it, and it pulls everything. It's only in science fiction that you see things are being taken in by black holes, the black holes going around the universe, swallowing things, etc. In fact, if the sun turns into a black hole, we are going to still go around the sun because the gravitational force is going to be the same. And it will be a very dark place. There will be no light from the sun, but even none of the planets are close enough to the sun to actually fall into the black hole, right? And the nearest black hole we know in the galaxy that exists is thousands of light years away from us, and they're not going to reach us. So don't worry. And our sun, when it ends its life in about 4 billion years, by running out of the hydrogen that it is fusing to produce light, is not going to turn into a black hole because it's not massive enough. It is going to collapse to form a white dwarf, which is also a compact star the size of the Earth, but it won't have the kind of gravity that you're thinking of.
Right, sir. So moving to the another question is, does light pollution affect the seeing of a planet? I mean, if there is more light pollution, does it affect the sightseeing of other planets, even using powerful telescopes?
Okay, I didn't talk about planets today, and so this is not quite relevant to what I talked about. But yes, you're absolutely right. Light, not only light pollution affects astronomical observations, but many things affect that. There are lots of things in space that are getting brighter and brighter that affects all this. What we do as astronomers is we choose places that are very high up in mountains and in very dry places. So I, for example, do all my observations in places like Hawaii or in northern Chile, in the middle of the Atacama Desert, on the Andes Mountains. That's where our best telescopes are. In the Australian desert, in the southern tip of South Africa, that kind of things. In India, the best places, there aren't very big telescopes, but the biggest telescopes are in Ladakh and near Nainital, in the foothills of the Himalayas, and in places like that. So there are places, these are far away from human habitation and light pollution and things like that. But even in places like this, light pollution is increasing. We have put telescopes in the Antarctica, for example, where there are very few penguins don't have light, and things like that. So we are trying, but increasingly we are putting telescopes in space. India has a telescope in space called AstroSat, the Hubble Space Telescope, Chandra, etc. They're all in space where light pollution is not a problem, but the problem is that we are also putting lots of satellites into space, and they create a lot of pollution in the space environment as well.
Right, sir. The next question is from Insa office itself. Karthikeyan is asking, can we see the Milky Way only through North and South Pole, or any part of Earth can see Milky Way through naked eyes, especially in India geolocation?
I should have a slide for that. Oh, you can see the Milky Way from India. The thing is, the Milky Way, as you know, is the center of our galaxy. It's a plane of our galaxy. We live in a galaxy, and we are about 20,000 light years from the center. And the central part is a very nice plane with the bulging up in the middle. Now, the Earth blocks from the northern hemisphere much of this view of the Milky Way, but we are very close to the equator, and it's best viewed from the southern hemisphere. But from India, we can see lovely pictures of the Milky Way if you go to a very dark site. You have to go very far away from city lights, sit in the dark for an hour or so, and then if you look up in the sky, you can see the Milky Way very nicely. Lots of pictures of the Milky Way taken from India. I would invite you to go to Google and search for pictures taken by Dorje Angchuk from Ladakh. He has taken some amazing pictures of the Milky Way from Ladakh, and so you can see that even as high as Kashmir and Ladakh, you can see lots of these lovely pictures. From southern India, also near Pune, we have gone to very dark places and taken lovely pictures of the Milky Way. So you can do that. Yes.
Right, sir. This is very informative to know. So we will take one last question. The question is about the LIGO project. How far is the LIGO project site in India away from the sea? Won't cyclone add to the noise? Why not choose a more naturally secured land like Madhya Pradesh or any other similar state?
Well,
Kind of a comment also.
we found a place. There are many things that went into choosing the site. In fact, the site survey itself took many years, and the short list was made of about 21 sites all over India from which this was chosen. It is as central as you can get, far away from the sea. Hingoli district is near Nanded in Maharashtra, and so it is eastern Maharashtra, not far from Madhya Pradesh. In fact, the second site and the third sites that were in our line were one in Madhya Pradesh and one in Rajasthan. But one of the main problems there is that you have to be far away from railway lines. And we looked at the railway network of India. It is very difficult to be 15 kilometers away from a railway line in India. And so finding such a place was difficult. In fact, the site we found in Madhya Pradesh, we found that there is a railway line being built through it in the next 5-10 years and things like that. So we found this final place, which is 15 kilometers away from railway lines. It is about 80 kilometers away from the nearest city, Nanded. It is about 10 kilometers away from the nearest small town. It is about a 6-hour drive from Hyderabad airport, about 9 hours from Pune, and things like that. So we need an airport, international airport nearby, but we don't want to be very near a big city. So that kind of stuff. So this is how we looked at ISRO's Landsat images of India to find out where we can place such a thing from the topology of the land, nearest habitation, etc. All that went. There was a very long process that this went through, and finally we found this place, which we are very happy with.
Right, sir. So in the meantime, we have got a frame question from Saurabh Vishwas. So if you're okay, we can take that question.
Yes, of course. I'm very happy.
Yeah. So he's asking, when the two black holes merge together, are new planets formed after these collisions?
I can't see how planets will be formed. As I said, when black holes actually suck in everything around them. So if there are planets around near it, that is. So I showed you that a black hole has a Schwarzschild radius. The kind of black holes that we are finding through LIGO detections are as big as Indian states, right? That there are hundreds of kilometers in size, and then if there were planets around them, they would have been sucked in. So this kind of effect of black holes pulling in things from around it goes to many hundreds of times its size. So out to a very large distance, if the black hole is a star that is part of something like the solar system, the nearest planets will be sucked in and things like that. So, but as I said, the Earth, it doesn't go in the solar system, our solar system, the effect will not go as far as the Earth. So when black holes are merging, if there are planets around these black holes, they will actually fall into this merging process. And so if nothing can be formed, of course, because everything goes inside the black hole. So as a result of the merging process, what only happens is that it creates a black hole that is even larger. And the distortion of space-time is going to be even larger. There's not a question of forming other things as a result, like planets.
Right, sir. So now, since we are already it's 12, now I would request Professor Saha to give some concluding remarks. Ma'am, you are.
Thank you, Dr. Rajuri, for a very interesting lecture. I just had one question. I don't even know if it makes sense. I thought the dark matter, if the dark matter has a concentration, will that influence the gravitational lensing?
Yes, of course. That is very interesting. Actually, a very, very interesting question. The dark matter, if it's evenly spread, will, of course, have a certain amount of light bending. But for example, in a galaxy, the matter is not evenly spread. It has a concentration towards the middle. And so as a result, the light bending from around it will have a characteristic profile. In fact, one of the things that we are trying to do is to find the shapes of dark matter inside galaxies and galaxy clusters from the effect that it has on the light bending. It is actually a whole new subject called weak gravitational lensing, where we look at hundreds and thousands of background objects and look at their distortions and statistically try to figure out from their shapes how the mass that is in front of us in this galaxy or in this cluster is the profile of the mass. And that is actually a very new subject. In the last 10 years, a lot of people are doing it. In fact, I have students working with me doing something like that. So it's a very interesting question.
That's very interesting. Thank you very much for being with us, spending your time with us. And this is my formal thank you to you. And I'm sure we would like to have you in future also as the LIGO project goes forward, and to know about the new developments in astrophysics. Thank you very much.
It's my pleasure. Thank you. Thank you for calling.
Thank you, sir, for this very informative session. At the end, on behalf of Insa-Inyas colleagues and on my behalf, I wish to thank Professor Somak again for such a fascinating talk, taking us away from COVID-19 and for sparing his time from his busy schedule. We believe that our viewers, in particular young researchers, have found it very useful and very informative. For the information to our viewers, we will meet again at the same platform in month of October with another eminent speaker, Professor Renu Savru, Secretary DPT. You can follow this discussion and further updates on official YouTube channel of Inyas. Until then, take care. Goodbye. Thank you very much, sir.